I want to discuss concavity and inflection points in this video. Okay? Concavity pertains to the bending of a graph. Okay? If a graph is bending up, if a function has a graph that's bending up, we say that the graph is concave up. If a graph is bending down, we say that the graph is concave down. Okay? One way that you can tell the type of concavity, the type of bending, is from the second derivative. The second derivative is the derivative of the derivative function. Okay? If something is concave up, it means that the second derivative is positive. If something is concave down, it means that the second derivative is negative. Okay, so why does concavity have to be related to the second derivative? Okay, so think about what a derivative is. It's the rate of change of a function. Okay, so the second derivative is the rate of change of the derivative. It's the rate of change of the rate of change. Okay, what does that mean? So the first derivative has to do with the slope. So apparently if the second derivative was big, it means that the slope is increasing really fast. Okay, can you see that if you have an increasing slope, it's getting steeper and steeper? That's going to be like the left example where it's bending up. Okay. On the other hand, if the second derivative is negative, that means that the slope, the steepness, is getting more and more negative. Can you see that that's going to correspond to the right example? Okay. So bending means that the steepness is changing. The instantaneous slope is changing. The slope of the tangent line is changing, either getting bigger or smaller. Okay, so here's an example of a function that is concave up everywhere. Y equal to x squared. What does that look like? So it's a parabola with a minimum at the origin, right? So let's look at the second derivative in that case. So y prime is 2x, y double prime is 2. It's always positive. It's always greater than 0. Okay. Example of a function that's concave down everywhere, where the second derivative is negative everywhere, is y equal to minus x squared. Okay, so for that example, y prime is minus 2x, y double prime is minus 2. So it's always negative. So it's always going to be bending down. All right. Now, concavity is useful if you're looking for local extrema. Okay? Notice that the concave up example corresponded to the bottom of a valley. Notice that the concave down example corresponded to the top of a mountain. Okay? So concavity can help you to find local extrema. When you use concavity this way, it's called the second derivative test. Okay? Let me go ahead and spell it out for you, the second derivative test, so there's no misunderstanding. Okay? Second derivative test. All right. So if the second derivative is positive at a critical point, then that critical point is a local minimum. Okay, hopefully that's clear. On the other hand, if the second derivative is negative at a critical point, then that critical point is a, wait for it, local maximum. All right, well, that sounds pretty good. So maybe we should just use a second derivative test when we always need to find local extrema. Well, I'm not a big fan of the second derivative test. I like the first derivative test better, okay? I like checking this derivative sign on both sides. Okay, why is that? Well, the second derivative test can let you down. Let me show you what I mean by that. Suppose you wanted to find the local extrema of y equal to x to the 4. Okay, well, so the parabola examples that I gave you, the second derivative at the local maximum for the x squared graph occurred where at a critical point where the second derivative was negative. For the minus x squared graph, the local minimum, the x squared graph had a local minimum where the second derivative was positive. The minus x squared graph had a local maximum where the second derivative was negative. Okay? However, that's all great, but that's not going to work for y equals x to the 4. Let me show you why. So y prime is 4x cubed. Let's set that equal to 0. Okay, so the critical point, we have one critical point. If we're focusing on all x values, so the closed interval or the interval for from minus infinity to infinity. I guess that's really an open interval, but let's look for not the absolute extrema, but just the local extrema. So the critical point, the only one is 0, 0. Okay, now great. So now let's find the second derivative at that critical point. So y double prime equals 12x squared. Plug in 0. What do you get? Y double prime of 0 is 0. So the second derivative test is not going to help you in this case. Okay? When it does work, sure, go ahead and use it. But don't act like a deer in the headlights when you get 0. Okay? The first derivative test, that's why I like it better. It won't let you down in all cases. Okay? Now, I want to finish this video by talking about something else called an inflection point. Okay? An inflection point is a point where the bending, the type of bending changes. Maybe it goes from concave up to concave down, or maybe it goes from concave down to concave up. All right? So an example of a point that has an inflection point is y equal to x cubed. All right, let's analyze the concavity for various regions for that graph. Okay, so what does the graph of x cubed look like? Well, something like this. Okay, so y prime is 3x squared, y double prime is 6x. So for positive x, we're going to get positive concavity. So for the first quadrant, right here, it's concave up, and we can see that from the type of bending. For negative x values, for the third quadrant, we're going to get concave down. Okay, now at the origin, the second derivative is 0. Okay, that is where the sign changes from, as you move to the right, from negative to positive. So that's our inflection point. Okay, to find an inflection point, it's similar to the first derivative test. You have to compare the sign of something on both sides of a point. Okay, in this case, you're comparing the second derivative on both sides. Now, let me emphasize something. We don't care about the first derivative when we're looking for inflection points. The first derivative is irrelevant. All right? The first derivative can be anything at an inflection point. Okay? You can have an inflection point. Let me show you a couple of examples. So the example I just gave you right now, the inflection point had a first derivative of 0, so it was a critical point, but an inflection point doesn't even have to be a critical point. All right. So for example, suppose that we had a graph that was shaped like this. Okay, so the inflection point, the type of bending is going to go from negative to positive around right there. But can you see that the slope is not necessarily horizontal there? Okay, so again, don't think about first derivatives when you're looking for inflection points. Okay, you can also have where the first derivative is undefined. Imagine you had something like the next example. Okay, so you see, so right here at this point, it's an inflection point. The bending goes from, as you move to the right, from positive to negative. Okay, and at the slope at the inflection point is undefined. So I gave you an example where the slope at the inflection point was 0, some positive number, and undefined. Okay, so all kinds of things are possible. All right. Now, what about the second derivative at the inflection point? Well, I gave you an example where the second derivative was 0 at the inflection point. The second derivative can also be undefined at the inflection point. Okay, that's let me write that idea down because that's important. The second derivative at an inflection point can be either 0 or undefined. Okay? If the second derivative is 0 or undefined, and if the second derivative changes sign as you move across the point from right to left, then you can be sure it's an inflection point. What would a graph look like that had an inflection point that had an undefined second derivative? Well, the green inflection point, the first derivative is undefined, so clearly the second derivative is undefined. Okay? So this one is the example with the undefined second derivative, the green one. All right?